Let me start, though, by reminding you what the main theorem was. So the main theorem, which is this joint theorem with Dan Thompson, who is very poorly lit in that picture, but there he is anyway, is that under certain conditions, and I'll write it here just so that it's visible throughout the talk. The first condition is that the obstructions to expansivity at a certain scale should have smaller entropy than the entire system does, than the topological entropy. And I remind you that when I say, do I have a pointer? I don't know. Oh, no, 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 no. There we go, I found it. So I remind you that by this, I mean you consider all measures with this non-expansivity property, the property that almost every point has a non-trivial bi-infinite Bowen ball, so it fails to be expansive. You take the supremum of measure theoretic entropies over such measures, and that's the entropy of obstructions. You want that to be smaller than the topological entropy so that every measure of sufficiently large entropy is behaving as is almost expansive. Then we need a decomposition. So you need a collection of prefixes, a collection of good words, and a collection of suffixes with the property that first it is a decomposition, meaning that every orbit segment of your system can be turned into a good word, the thing in the middle, by first cutting a prefix from the front and a suffix from the end. So this needs to be a decomposition. It needs to have the property that GM has specification at scale delta. Specification is just this property that given an arbitrary collection of orbit segments from GM, you can glue them in a uniform time. GM means that the prefixes and suffixes are less than or equal to m in length. And the final condition is that these prefix and suffix collections should have smaller entropy than the whole system. Where, once again, I remind you that by this, I mean that you count the number of prefix, suffix, orbit segments of length n, which are distinguishable to scale delta. So you cover it by n delta separated set, or spanning set, I guess, and then you take the growth rate. Under those conditions, there's a unique MME. So that's the main theorem, which we spent the last 2 lectures discussing. And now I go to the slides and tell you some applications of this. Although first I point out that if you don't like thinking about proving that every GM has specification, it's, I left a very important thing off, which is that there's this relationship between epsilon and delta. So you should have epsilon, I think here I said equal to 28 delta, that's okay. Greater than is also fine. But if you don't like thinking about these scales with this funny relationship, it's okay to just consider the entropy of obstructions to expansivity as being the limit as epsilon goes to 0. And you can prove, if you prove that G has specification at every scale, then it follows that GM has specification for every M. It's just a continuity argument. Okay, so there's a scale-free, the point is that there is a scale-free version of this which will apply for the first 2 examples I give, which are to partial hyperbolicity and to billiards, but the version with a scale will be necessary for the 3rd example, which is geodesic flow and no conjugate points. So let's look at the examples. So the first one to discuss is motivated by this Magnier example on the 3 torus. You start with a hyperbolic toral automorphism F0. This is linear, it has 3 real eigenvalues, all of them positive, 2 of them smaller than 1, 1 of them larger than 1. And so of course you have this kind of picture. And near some fixed point, Q, you take a ball, and inside that ball you make a perturbation. The perturbation is done along the center, along the stable direction, so the weak stable direction. And it's a pitchfork bifurcation so that now the index of Q changes. the center, this middle direction becomes expanding at Q, and you create two new hyperbolic fixed points with the same index as Q originally had. And you ask what you can say about the new system. And plenty of people studied this. Monnier introduced it quite a while ago. In fact, it was already known that this system has a unique measure of maximal entropy. Raul Rores gave one proof. Another proof was by Buzzi, Fisher, Sabrino, and Vasquez. But we are going to study it anyway because we can give an alternate proof. It illustrates our methods, and also because if you read our paper, you see that the methods actually tell you about not just the measure of maximal entropy, but also equilibrium states for non-zero potentials, which is a little trickier, and which was not in these previous papers. So,
for all potentials?
No. Not for all potentials. There is some condition. I will not talk about it. You can ask Dan next week. He's talking about equilibrium states. So, we need to talk about expansivity, and we need to talk about specification. So what are the expansivity properties of this example? The first thing to observe is that it is not expansive. Suppose I consider, well, okay, so in fact we consider not just this diffeo F, but in fact a C1 perturbation of it. And everything which I say is true is a C1 open condition. So you take some C1 perturbation, it's partially hyperbolic, there's a one-dimensional unstable, one-dimensional center, one-dimensional stable. The stable and unstable foliations are minimal, and it is known that the center one is integrable. So that's very nice. However, it's not expansive, so that's kind of bad news. The reason it's not expansive is that if you consider the piece of center joining the original fixed point to one of the new ones, then any point on this manifold goes to P in the future and Q in the past. On this leaf, it's behaving like the time one map of a flow. So so you have plenty of points on that leaf which stay close to it for all time. The good news is that this is more or less the only thing that can happen. By more or less the only thing that can happen, I mean first, that the standard argument for expansivity shows that the bi-infinite Bowen ball is always a subset of the center leaf. So the stable and unstable directions, things still escape, there's no problem. So if you want to understand which points are expansive, then you should understand the center exponent. You should understand how much expansion contraction there is in the center direction. So let's let phi c denote the log of the derivative in the center direction. Working with one-dimensional center, the main reason we want to work with one-dimensional center is that then this is just nice and additive and you don't have to worry about these mostly expanding, mostly contracting kinds of conditions. And we can just take the Lyapunov exponent, the center Lyapunov exponent of an ergodic invariant measure by integrating this. And if you have an ergodic invariant measure for which this center Lyapunov exponent is less than -r, so it has some non-uniform contracting property, then for almost every point, the average of phi c is in both forward and backward time less than -r. That's simply Birkhoff. And this is continuous. It's compact, so it's uniformly continuous. So you can choose an epsilon, depending on r, such that if another orbit remains within epsilon of u for all time, then the average is less than, say, -r/2, and that gives you enough contraction and expansion, well, in this case, I guess, yeah. That gives you enough hyperbolicity on the bi-infinite Bowen ball to guarantee that that is, in fact, a single point. And so every point with this, every measure, every ergodic measure with this property is almost expansive. So let me say it again. And let me say it in a more general setting, because that argument does not rely on the structure of the Monnier example. That argument simply relies on having a partially hyperbolic diffeo with one-dimensional center which is integrable. So over the next few slides, I'll introduce a few assumptions on a partially hyperbolic diffeo. Those will be in green to say what the assumptions are when we introduce them. And the argument from the previous slide says that if you fix an r greater than 0, then there's some epsilon such that any ergodic measure whose center exponent is greater than r in absolute value, so either it's less than -r, or it's greater than +r, then that measure is almost expansive at scale epsilon. And another way of saying this is that the entropy of obstructions to expansivity at scale epsilon is bounded above by the supremum of the entropies of such measures. So this gives a nice bound. And then some argument, which is outlined here, shows that as you send epsilon to 0, this converges to the supremum of entropies of measures with 0 center exponent, so that these are the obstructions to expansivity. And the argument is a simple one using upper semi-continuity of the entropy function and just convergence of some sequence of ergodic measures. So that's the takeaway from this slide. For this class of systems, the obstructions to expansivity are measures with 0 center exponent. Every other measure is almost expansive. In particular, if you go back to think about the Monnier example, how can you have a 0 center exponent? Well, let me go back to the picture. The center direction is contracting uniformly everywhere outside the pole of the perturbation. So the only way to have a 0 center exponent is if you spend almost all of your time right here. That is not a good way to produce entropy. So the conclusion is that every ergodic measure for the Monnier example, which has 0 exponent, is going to have small entropy, and you can make all of these estimates precise. But it's a little more painful, so I won't. So that's the idea to controlling entropy. Now let's talk about specification. We're going to need a decomposition. So suppose we're in a situation like the Monnier example where most orbit segments have contraction along the center direction at some kind of asymptotic level. Okay, that's a very vague assumption. I will make it precise in a moment. Then let's fix an r greater than 0, just as we did before. And now instead of considering the measures which so last time we considered the measures which did not contract by more than r in the center. So they did not have strong enough contraction, or maybe they even had expansion. Now I want to consider the orbit segments with this property. I want to consider the orbit segments which do not contract by more than r in the center direction from start to end, on average. Do not contract. The average rate of contraction is not what it should be. I claim that this serves as the prefix collection in a decomposition which does everything I want. So what should the decomposition be? The decomposition should be to take an orbit segment xn, this is this guy here, look at each time p, and look at the orbit segment that goes from x to p. So 1, 2, 3, 4, and so on. And for each one of two things will happen. Either it will be contracting quickly enough, so blue is good, these are the good guys, or it will not be contracting quickly enough, and it's bad, and this is the red guys. So you have some good guys, some bad guys, fine. Take the longest bad guy. So this is p of xn. And of course that original guy is in CP, your prefix collection, that's just the definition. But now I need to say something about the rest. I need to say something about this orbit segment. And the nice consequence of the way I defined these blue and red pieces, this good and bad stuff, is that if I take two bad pieces, so two orbit segments along which the average rate of contraction is greater than or equal to minus r, well, of course, the same is true of their concatenation. So suppose any of these guys was bad, was red. Well, then the longer thing from here would also have been red, which would contradict maximality. So it follows that every initial segment of this second half here sees uniform contraction. So if you're used to this kind of stuff, you should look at this and you immediately think that I'm talking about hyperbolic times. And indeed I am. This is a hyperbolic. This is exactly analogous to the notion of hyperbolic times introduced by Alves. So this is our collection of good orbit segments. An good orbit segment is one for which from the beginning to anywhere in the middle, you see a uniform rate of contraction given by r. And there's no suffix collection here. The reason there is no suffix collection is because the unstable is uniformly expanding. So the idea now is that we should be able to estimate the entropy of these prefix collections and verify condition 2, and we should be able to prove that the good orbit segments have specification at any scale and verify condition 1. So the argument for entropy of the prefixes, once again, goes by getting some relationship to the entropy of invariant measures. So you remember, if you recall when I originally talked about the variational principle and Bowen's proof of uniqueness, there was the standard construction of a measure of maximal entropy. And it went by taking a maximal n epsilon separated set and getting an equidistributed measure on it and averaging that through time n and taking a limit. So it's this standard construction. And that construction works even if you don't take a maximal n epsilon separated set. It just doesn't give you a measure of maximal entropy anymore. But what it does do is it gives you an invariant measure whose entropy is at least as big as the collection of orbit segments you used to build it. So let's do it now, not with the whole collection of orbit segments, but with the bad guys, with the prefixes. So if I use these prefix orbit segments, which I recall are the ones for which the Birkhoff sum, the Birkhoff average in the center direction is at least minus r, run them through this construction, you produce an invariant measure with two properties. First, okay, I put them in the wrong order. First, its entropy is at least the growth rate of these guys, the entropy of CP, by the standard argument from the proof of the variational principle. Second, because this phi c is continuous, and these guys, these empirical measures converge weak star, or rather the convex combination of them converges weak star to your mu, and the average with respect to any of the empirical measures is at least minus r. The same is true of your limiting measure. So your limiting measure has center exponent at least minus r. And then by the same argument as before, by the same argument as on the previous slide, what am I saying? Yes. So I'm now claiming that there's some lemma. And the first piece of it is this inequality. So this inequality is what I just argued, that the entropy of the prefix collection is bounded above by the supremum of the invariant measure's entropy, for which the center exponent is at least minus r. And now in order to have a way to write that down, I use the same kind of limiting argument as r goes to 0 as on the previous slide. I define some quantity h plus. This is the supremum of entropies taken over all invariant, here I should specify here that this is, this is all invariant, not necessarily ergodic. This is all invariant measures with non-negative center exponent, so that's the plus. I take the supremum of the entropies, that's the h. So if h plus is strictly less than the topological entropy, then the same kind of limiting argument from the previous slide says that this supremum is also less than the topological entropy for a sufficiently small r.
Why is it strictly less?
Why is what strictly less?
H plus strictly less.
This is an assumption. Okay. Suppose you know this. Okay. This is what we need to find from somewhere else. Okay, yes. Okay. Suppose you know this from wherever. Then you have a gap between the entropy of the prefix collection and an entropy of the whole thing. And that's this condition too. So your small prefix collection condition is satisfied. And now all that is left is the specification condition. Well, remember how we argued for specification last time? Let me just draw the cartoon. The cartoon was that you should do a gluing process where you take a unstable here, you push it forward, you get some longer thing. No, it doesn't go through there, but it intersects the stable through there. And that's your shadowing point when you pull it back, because when you push it forward, it shadows, and when you pull it back, it shadows. That was the argument. And when I made that argument, I pointed out that you were only using one property of the stable direction. So here we want to run the same argument, but we want to use the center stable. The center stable does not have uniform contraction. But all you need is to know that a ball in the center stable is contained in the Bowen ball for this particular orbit segment. And that is true if it's a good orbit segment, because the condition of being in G is the condition that along any initial part of the good orbit segment, you have uniform contraction. That means that if you take a piece of center manifold of length delta, it contracts like this. I mean, it may get smaller at some points and then get bigger, but this is an upper bound. And in particular, this means that the delta ball in the center stable is contained in the Bowen ball, and that's enough to recover the specification argument, and that completes the proof. So let's summarize. if you have a partially hyperbolic diffeo on a compact manifold, if the center dimensional is one stable, if the center direction is one dimensional and integrable, if all of the unstable leaves are dense, and if this quantity H plus is less than the topological entropy, if you can prove that somehow, then there's a unique MME. And of course, the same thing is true if you reverse stable and unstable. So if you have a dense stable, and if the entropy of things with non-positive Lyapunov exponent is bounded away from the topological entropy, then it's enough. 3 comments about this theorem. 1, it applies to Magnier, as long as the perturbation is small enough. 4 comments. 2, there is a corresponding result for equilibrium states. 5 comments. Sorry, the 4 and 5 are what's written. The other comment I should make is that the argument for this is in my paper with Todd Fisher and Dan Thompson, where we study the Magnier example, but it is not written this way because we only wrote it for the Magnier example. But the proof goes to this setting verbatim. I mean, which, because we were thinking about the Magnier example, we didn't really realize at the time, but later it became clear. Remaining 2 comments. This condition that you need is that either H plus or H minus is less than the topological entropy. There are 2 equivalent ways of formulating that, which you may or may not find useful. One way is that they should be different, because the topological entropy, by the variational principle, is the maximum of them. So you want the minimum to be smaller than the maximum, so they should be different. This condition, if this condition fails, then these 2 numbers are equal, and one of 2 things must happen. Either there is an MME which has 0 center exponent, or there are at least 2 ergodic MMEs, one of which has positive center exponent, one of which has negative. And Katrine Gelfert can tell you all about examples like that. I cannot. The other equivalent condition to this is that if you consider the pressure function given by multiples of the center geometric potential, then this condition is equivalent to asking this pressure function not to have a minimum at 0. So if any of those is a easier condition for you to think about, then please use it. The final, yes?
What is involved in showing that the Magnier example satisfies the hypothesis?
Unpleasant entropy estimates. They're in the notes for lecture 2, actually, because at some point I thought I may say something about them and then decided I didn't want to subject us to that.
Can you explain the minimum pressure?
Sorry?
The minimum pressure.
This one? So, suppose your picture is like this. Then, if there's some T for which the pressure is less than the entropy, then any equilibrium state, any measure of maximal entropy has a center Lyapunov exponent, which is the slope of a subtangent line to this function at 0. In this picture, those must all be positive. That's the idea. One more comment on this example before I go to billiards, which is that you don't actually need integrability of the center direction. And it just goes to the specification argument here. The argument that I gave said, take the actual center stable manifold here and push it forward and see that it contracts. But it works equally well to go to the end of the orbit, take an admissible center stable, that is just something which is tangent to the continuous cone families, which you have in this example, and push it backwards, and see that it expands. So the argument works without the assumption of integrability. You just have to be a little more careful in how you prove specification. And there's a similar thing for expansivity. That is all I want to say about the partially hyperbolic case. Are there any questions about it before I move to the billiards? Okay. So I assume we're happy for the time being. So now let me talk about the billiard map for the Bunamovich Stadium. So this is much easier to deal with in many ways than the CNI billiard that Vivian has been talking about, so my job is much easier. And first, let's just recall the setup. So you have this billiard table, Bunamovich Stadium, which is two semicircles glued to the ends of a rectangle. And you consider the billiard map, which takes one collision to the next collision. The information on a given collision is given by two parameters, r and phi. R tells you the location along the boundary of the table. Phi tells you the angle that the direction makes with the normal. That angle can be anywhere from -π/2 to +π/2. It's an open interval. So your phase space is this direct product. Of course, the boundary of the table is topologically a circle. So the phase space is an open annulus, which is represented here. The left and right boundaries should be glued together. The top and bottom boundaries are open. And you see that if you have a point r phi like this, so here r is in y2, so it's along the bottom. It's close to the right end point of it, it's this point here. Phi is positive, and it gets mapped up here. It hits gamma 1, and now at this point, r is in gamma 1, and phi is again positive in this example, so it's up here. So you have some map from this open annulus to itself. Now this is a problem for applying our theorem, because the very first assumption in the theorem was that you have a compact metric space and a continuous map. This is not a compact metric space. Okay, well that's fine, you compactify it. So there's an obvious way to compactify it, which is just to replace this open interval with a closed one. So you close the rectangle, and that appears to work fine, except that now you've introduced some discontinuities. If you think for a few minutes about what's happening at these 4 points. Look at this point here where y2 joins gamma 1. At this point, if I have a collision here which is pointing to the left and approaches π/2, and the base point is approaching this from the left, then it runs all the way to the other half, and so the limiting point should be this guy here. On the other hand, if I come in from the right and my collisions are close to π/2, then I should get a fixed point here. So the limit does not exist. So there's no continuous extension of the billiard map to this obvious compactification. There are 4 discontinuity points, 1 at each of these join points. So instead we compactify in a different way. You just take a 2-point compactification where you collapse the top and the bottom into single points. And those are fixed points for the map F extends to the compactification by declaring both of those to be fixed points. And now you have a continuous map, and in fact the compactification is a sphere because you started with an annulus. So you have a map on the sphere. It's not, the relationship between this and the original system is that the space of invariant, ergodic invariant measures is the same except for these 2 delta measures on fixed points, which make no contribution to the problem of an MME, so you can ignore them. So if we can prove MME for the continuous extension, it's enough for the stadium. And that's what we do. So the theorem, this is joint work with Jianyu Chen and Hongkun Zhang. It is preliminary in the sense that we've written half the paper, but there are still some details to write down. The theorem is that the Bunamovich Stadium map has a unique MME. And to see how it follows from the general theorem over there, I need to introduce the following collection of orbit segments. Consider the regular, fix a parameter eta, and consider the set of points r phi, where your distance from the flat part is at least eta, and your distance from π/2 is at least eta. So it's these green rectangles here. It has 2 connected components. I want to consider, so these are collisions not with the flat parts, but with the circular parts, which are what generates hyperbolicity. And I also want to consider orbit segments that cross the stadium at least once, by which I mean they hit both of these connected components of r eta. And then you can define some cone families. There's a global coordinate chart here, so there's a global choice of coordinates on the tangent space. You can define some cone families here, which the people who know billiards, such as my co-authors, assure me are invariant under the derivative map along such orbits when you go from the start to the end. So you have invariant cone families, you get uniform expansion estimates, and very briefly, without describing all the details, that together with transitivity is enough to prove the specification property for this collection G. And you basically use the same argument. So that tells you that there is a collection of good orbit segments. The next thing you need is to find a prefix-suffix collection to have a decomposition. And you need to say something about obstructions to expansivity. Well, if the good guys... Yes?
So you said that the uniform hyperbolicity plus transitivity gives specification?
Yes.
What do you mean in this particular
In this particular case. This is not a universal principle. Yes, because you need, if you want some kind of universal principle, you need a much stronger version of transitivity. Here I'm benefiting very greatly from the fact that there is this continuous cone family on a neighborhood. That gives me that's a very strong assumption. So, to define a decomposition, the good things were the things which start and end in a particular region, so I should consider as the prefixes and suffixes the things which always remain in the complement of that region. So C is the collection of orbit segments which for their entire duration are outside of R eta. So they're either hitting the flat part or they're hitting the curved part with an extremely small angle, or angle very close to a pi by 2 or negative pi by 2. And then this is a decomposition, because if you have an orbit segment, you simply take the first time at which it enters R, the last time at which it enters R, and that's a good piece in the middle, and the guys on the end are in C. So it's very easy to prove that this is a decomposition. And then there's a similar kind of argument to prove that the entropy of C can be made arbitrarily small. It's very similar to the one I gave for the partial hyperbolicity case. You follow the standard measure of maximal entropy construction. You build a measure whose entropy gives an upper bound for the entropy of C, and in fact that measure must be supported on the complement of R eta. But the complement of R eta is just the flat parts and the pi by 2 parts, and roughly speaking, there's no entropy there because all of those orbits are just fixed points and period 2 orbits. So, by making eta small enough, you can guarantee that the entropy of the suffix collection is smaller than the topological entropy, which is known to be positive. And using a similar then using some similar arguments and the lemma on G and some Poincare recurrence argument, you can show that the entropy of obstructions to expansivity is also 0, which is the idea of the theorem.
I have a question
yes.
about this. When you made it into this complexification,
Yes.
you didn't change the topological entropy.
It's the same. So it depends what you mean by topological entropy for the non-compact system. Okay. If you mean the supremum of the metric entropies, then I did not. Okay. If you mean something else, then we should think about it. Any other questions about the billiard example before we go to geodesic flow?
So for time, if you consider continuous time, you can consider...
For the billiard flow on Bunamovich? Yeah, same story. Yeah, the same story.
And so you don't know that this measure is admissible? Or?
We cannot prove that this measure is adapted in the sense that you need to lift it to this Markov shift that Yuri and Carlos Mateos build. Although we also haven't had very long to think about it because this is very recent. Okay. So let's talk about geodesic flow. And of course, if I'm going to talk about flows, then we should have a general result for flows. It's basically what you think it should be. There's a result for maps. At every point, you replace n with t, and you get a theorem for flows. There's a couple places where it's a small subtlety. I will point them out. Okay, 28 becomes 40, fine. The definition of obstructions to expansivity changes a little bit. Because for a flow, of course, there are always points which remain nearby for all time. They're the ones on the orbit, very close to you. And so the definition of obstructions to expansivity should instead require that those be the only ones. That's the only change there. By the way, this differs a little bit from the original definition of expansivity for flows, which allowed some reparameterizations of the orbit, but this is enough for us. And then you assume you have this decomposition. The space of orbit segments is now x cross positive real numbers because that's your time. You assume specification as before. And there's an annoying technicality in the definition of how, in the condition you actually ask for here, which is that instead of taking 1 over t and considering things of length exactly t, you should consider things that are close to t. Okay, fine. It's a small technicality which doesn't affect any of the explanations, so I will ignore it and move on. So let's talk about geodesic flow. We begin with a closed Riemannian manifold M. All of the manifolds I consider will be compact. If you want to talk about non-compact manifolds, I cannot tell you anything yet. So that's a standing assumption. Everything is compact. And then on the unit tangent bundle, we have the geodesic flow Ft. This is defined by taking a unit tangent vector. It generates a unique unit speed geodesic, which is initially tangent to it. You move time t along that geodesic, that is and the tangent vector there is the image under the flow of V. And the hyperbolicity properties of this geodesic flow are associated to the curvature properties of the manifold. When the manifold has negative sectional curvatures at every point, then the geodesic flow is Anosov. Indeed, this is sort of the classical example of an Anosov flow. And that's kind of pictured here where you see things diverging quite quickly. Whereas if you have zero curvature, then things can run in parallel and not separate. And if you have positive curvature, then you get some kind of focusing properties. So this is the story. And the tool, well, one of the main tools you use, okay, you talk about Jacobi fields and various other things, but since I want to just draw pictures and not write equations, I will talk about horospheres. So in negative curvature, the idea is to work in the universal cover, which we denote M tilde. You have an ideal boundary, so the universal cover is, of course, a ball. It's homeomorphic to Rn. The ideal boundary is homeomorphic to the sphere of 1 dimension less. And in negative curvature, there's this nice correspondence between the stable and unstable manifolds associated to a vector and the normal vector fields to the horospheres. So given any vector, you can extend it. It connects 2 points on the ideal boundary. Then you consider all the geodesics which terminate at this point on the ideal boundary. You have some Boseman function which tells you how to parameterize things, and then you have some horosphere which consists of a bunch of points flowing towards, well, which remain within bounded distance. And in fact, in negative curvature, they converge to each other. So you get really the stable and unstable manifolds. That general picture persists even when you move beyond negative curvature, at least for a while. But there are some problems. If you, for example, suppose you flatten out your negative curvature along a cylinder, then you get a family of geodesics, these red guys here, which correspond to the same points at infinity. And so, in fact, their horospheres have a non-trivial overlap. So that kind of thing can happen. Or even when that doesn't happen, you could have higher order tangencies which correspond to the stable and unstable directions making zero angle with each other. So I should emphasize that when I say stable and unstable here in the following slides, it's not quite the same as saying stable and unstable manifolds in the sense of Pessin theory, because these Ws and U in my setting will always exist at every point, whereas the ones in Pessin theory only exist almost everywhere. Now, when the ones from Pessin theory exist, then they agree, at least on some neighborhoods. So it's reasonable terminology and notation, but there is that caveat. So what lies beyond negative curvature? Well, of course, the next step is to allow the curvature to vanish at some points. So you go to non-positive curvature. And in non-positive curvature, no, let me not say anything about the properties yet. Let me just say the 4 different regimes. So once you start to allow a little bit of positive curvature, you can still recover very good properties by imposing a no focal points condition. No focal points is equivalent to the statement that in the universal cover, balls are convex. And you can go beyond that and look at no conjugate points. No conjugate points is equivalent to the statement that any 2 distinct points in the universal cover determine a unique geodesic segment which connects them. If you go beyond this, I cannot tell you anything about hyperbolicity properties of geodesic flow. There are some examples, but this is sort of the broadest setting in which you have globally good tools. Although, as you'll see in a moment, the tools in no conjugate points are fairly limited. One thing that I do want to point out based on this fact, because this is in some sense the key property of no conjugate points that we use, is that there's a bijection between the space of orbit segments for the geodesic flow and the set of pairs of distinct points in the universal cover up to moving the pair by a deck transformation. And that correspondence will come in very, very useful a little bit later. But first we should survey what's known for geodesic flows. So you have this hierarchy from negative to non-positive to no focal points to no conjugate points. Well, the negative curvature case is Anosov, and so this was handled in the 70s. You have Bowen-Margulis measure. Bowen-Margulis measure for geodesic flow and negative curvature is the unique measure of maximal entropy. And there's also a theory for non-zero, for every Holder continuous potential in that negative curvature setting has a unique equilibrium state. Going beyond that took a little while, and in 1998, Knieper proved that, in fact, in non-positive curvature, you have a unique measure of maximal entropy subject to a rank 1 condition. Never mind what it is. His proof used some different techniques from the classical ones. It used Patterson-Sullivan measures rather than anything using expansivity specification or coding by Markov shifts or anything like that. His proof also didn't say anything about equilibrium states for non-zero potential functions. Whether that's because it can't or whether because he didn't bother, I'm not entirely sure. But at any rate, it left something for us to do. A few years ago, we started thinking about this problem of applying this general result using expansivity and specification in the setting of non-positive curvature. So that was a joint project between Keith Burns, myself, Todd Fisher, Dan Thompson. You can see us there, although I apologize for not standing in alphabetical order. And that result does cover some non-zero potential functions. Dan is going to talk about this next week. In fact, I think all 3 of Dan's talks next week will have to do with this example. So I'm going to leave that for him. And I want to mention what happens beyond non-positive curvature. So the next step was no focal points. And in no focal points, the first result that I'm aware of was a result by Katrine Gelford and Rafael Ruggiero, which proved uniqueness of the measure of maximal entropy in dimension 2. And this used Bowen's techniques. Though he used them in a way that's a little bit surprising to me by finding really a conjugacy to something which is, a time-preserving semi-conjugacy, is that right? Yes, a time-preserving semi-conjugacy to a expansive flow with specification. And even though the date here is after these dates, that's because these are archived and that's the journal. Then, I don't know if these are simultaneous, but they were going on around the same time. These 3 guys proved that they generalized Knieper's proof using Patterson-Sullivan measures to show that for no focal points you have a unique measure of maximal entropy, and it works in any dimension. Meanwhile, these 3 guys, I think Kehoe is here, proved that you can extend our approach via specification to cover some non-zero potentials, at least in dimension 2. And they're working on higher dimensions, I understand. So again, I'm not going to say anything more about the no focal point setting. I want to talk about the no conjugate point setting, where the theorem is, if you have a surface of genus at least 2 without conjugate points, then there's a unique MME. And this is archive preprint with myself, Gerhard Knieper, and Kadim War. And since I am leaving tomorrow morning, if you have questions, you can ask Kadim next week. So, to say a little more about these different settings, we should look at some of the properties they have. So there are various things that you might wish to look at in the universal cover. You may wish to look at 2 geodesics which begin at the same point and move in different directions. And you may wish to see whether they diverge and how quickly they diverge. If you're in negative curvature, they diverge very well. The distance between them is strictly convex. If you're in non-positive curvature, well, the distance between them, it's convex. And that actually plays a very important role in some of the proofs of BCFT. If you're in no focal points, now they're not convex anymore, but they're at least monotonic. So these points are moving, 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 and okay, they at least don't get closer together at any point. But this failure of convexity is responsible for some of the difficulties these guys had in extending it to no focal points. And then in no conjugate points, you know that this distance is positive. So the points start like this, they wander off, maybe they come back together, but they don't meet. But they could get arbitrarily close. And then they wander off again. Okay, so you don't have too much. Well, we want to work with horospheres, because horospheres are the sort of the tool for hyperbolicity. And in negative curvature, horospheres are strictly convex. In non-positive curvature and no focal points, well, you might lose strictly, but they're at least convex. In no conjugate points, maybe they are, maybe they aren't. I'm pretty sure there are examples. Yeah. So you may want to look at how these stable and unstable directions depend on V. These are the normal vector fields to the horospheres, or they're determined by the normal vector fields to the horospheres. And in negative curvature, it's Anosov, so the stable and unstable directions are whole or continuous. It's the classical theory. And in non-positive curvature and no focal points, well, maybe they're not Holder anymore, but they're at least continuous. And that is a very important part of the proof, at least of our proof in the non-positive curvature setting. And in no conjugate points, maybe they're continuous, maybe they're not. There are examples. The dinosaur example from Ballman, Brin, and Burns is one. What if you consider two geodesics which hit the same point on the ideal boundary? In negative curvature, that means they're the same geodesic. Okay, maybe a reparameterization. So there's a unique geodesic connecting any pair of points. In non-positive curvature and in no focal points, there's a flat strip theorem, which says that, okay, you can have different geodesics going to between the same points at infinity, but only in a very prescribed way. There's a flat strip theorem. If you have two geodesics like this, then in fact, they bound a strip where the geometry is literally just flat. And in no conjugate points, there are counterexamples showing that this is not always true. So, at this point, it looks like we lost all our tools. What are we going to do? We don't have the tools that we would like to use in these other settings, so do we have anything left that we can use? So let's start an inventory. What do we know about no conjugate points? Well, the first statement is that in no conjugate points, the universal cover is still a disk. Every pair of points is connected by a unique geodesic. That's true in any dimension, requires nothing more. If you're in dimension 2, then the ideal boundary still makes sense and you can still talk about horospheres. You can do it in higher dimensions too, but you need an extra condition. So let me only talk about dimension 2 for the moment. Okay, now here's a couple things which require a little bit of explanation. Because the conclusion of these next 2 points will be that the entropy of obstructions to expansivity at a certain scale is 0. That's a very good thing, because that's the kind of thing we need for our theorem. So the first observation, and now I'm going to use dimension 2 again. If you have an ergodic measure of positive entropy, then it has non-zero Lyapunov exponents, Margulis-Rouel inequality. Therefore, by Pessin theory, the stable and unstable manifolds have trivial intersection almost everywhere. By trivial, I mean they intersect in a single point, as you expect. But if the stable and unstable manifolds intersect in a single point, then the stable and unstable horospheres must intersect in a single point. If the horospheres would overlap more than that, then you would have non-trivial intersection between the stable and unstable manifolds. So that's one observation, is that for every positive entropy measure, you have trivial intersection between the stable and unstable horospheres almost everywhere. Hold that in your mind. Second observation. Suppose I have 2 vectors v and w, whose orbits under the geodesic flow remain within, say, 1/3 of the injectivity radius of the manifold for all time. Then I lift them to the universal cover, and I get 2 geodesics in the universal cover with the same property. That's why it's important that I ask them to be less than the injectivity radius. If I increase that number, then when you lift, you could sort of wind around in strange ways and maybe you lose this. So you lift to 2 geodesics in the universal cover, which remain within a bounded distance Well, if they remain within a bounded distance, that's the definite. I never told you what the boundary at infinity is. But that's one characterization of it is geodesics which remain within a bounded distance. So if you have 2 points that remain, 2 geodesics that remain within a bounded distance for all time, then they correspond to the same pair of points on the ideal boundary. That means that either they're on the same geodesic, or you have a non-trivial intersection between the stable and unstable horospheres. Now, putting these two pieces together, we can deduce that the entropy of obstructions to expansivity at this scale is 0. Because if you have a non-expansive measure, then it has this property almost everywhere for some w which is not on the orbit. Therefore, you have this non-trivial intersection. Therefore, you reverse the arrows here and take the negations, and you get 0 entropy. So that's a very good, that's a promising sign. We have 0 entropy of obstructions to expansivity at scale 1/3 the injectivity radius. Yes? Yes. So I will go very quickly through the remaining ideas. The remaining ideas are as follows. There's another metric on your surface of genus, at least 2, which has negative curvature. There's a Morse lemma, which tells you that given a no conjugate point metric, a negative curvature metric, and a pair of geodesic segments on the universal cover, one for each metric that start and end in the same place, there's a uniform bound on how far they are apart. You can use that to take the specification property in the negative curvature metric, take an arbitrary collection of orbit segments here, turn it into a collection of orbit segments here, shadow them, move back. Now you have specification for the original guy. But you have it at some big scale, 3r. And r is probably large. R is probably much larger than the injectivity radius of the manifold, so you cannot expect to apply the theorem. And so we are saved by a property called residual finiteness, which applies to every 2-dimensional manifold, to the fundamental group of any 2-dimensional manifold, and says that you can take a finite cover with an arbitrarily large injectivity radius. In particular, you can take its injectivity radius to be larger than what you need to apply the theorem. And because it's a finite cover, there's an entropy-preserving bijection between the spaces of invariant measures. And so your unique MME upstairs gives you a unique MME downstairs. And that's it. So there's some extension to higher dimensions, but it requires various assumptions. And I'll just point out that because of this trick of doing things at a very large scale and in a coarse way, I have absolutely no idea how you could extend this to any non-zero potential function. I have no hyperbolicity properties. I have no idea how to verify the Bowen property. But I never told you what the Bowen property is. So I'll leave that for Dan next week, and I'll stop there.